essentially using the general solution to the special case. So recall that if we have 1 plus alpha times x minus x naught squared times y double prime plus beta times x minus x naught times y prime plus gamma times y equals 0, that this differential equation has solution y equals the sum from n equals 0 to infinity a sub n times x minus x naught raised to the n. I need to update my screen. The power series solution in x minus x naught, where a0 and a1 are constants. In the real numbers, and a sub n plus 2 is defined by doing negative alpha times n minus 1 plus beta times n plus gamma over, so the negative out front, the alpha all the way through gamma being divided by n plus 1 times n plus 2. And that whole fraction multiplying a sub n. So let's go ahead and try to use that to find the power series solution in x minus 2 to x squared minus 4x plus 2 multiplying y double prime plus negative 6x plus 12 all multiplying y prime plus 4y equals 0. So the very first trick, anytime you want to find the power series solution in some specified at x minus x naught, is to try rewriting each of those polynomial coefficients in powers of x minus x naught. So as a general rule, when looking for a power series solution, in x minus x naught, rewrite the polynomial coefficients in powers of x minus x naught. So there are a few ways to do this. One option is to just try completing the square and go from there. Another option is to just essentially replace all x's with x minus x naught and then plus x naught. So to do this, we can replace all x's with x minus x naught in parentheses and then plus x naught. So in this case, we're going to do that with x minus 2. So that first polynomial, x squared minus 4x minus 2, plus 2, we can rewrite this as x minus x naught, x minus 2, and plus x naught, that whole thing squared, and then minus 4 times x minus x naught. I keep replacing my x naughts with forgetting to replace my x naughts. So that first one should have been x minus 2 and then plus 2 and then that whole piece squared. Then minus 4 times x minus 2 and then plus 2. And then we just have plus 2. So this we are looking at x minus 2 squared. Then we would have plus 4 times x minus 2 plus 4. That next piece becomes minus 4 times x minus 2 and minus 8. And then we have plus 2. So our plus 4 times x minus 2 and minus 4 times x minus 2 just cancel each other out. And this becomes x minus 2 squared and then minus 2. You can always try completing the square and take that route as well. This is just an alternative method. Our second polynomial was negative 6x plus 12. So I can just tell right off the bat that that should be negative 6 times x minus 2. And then, of course, 4 is just 4. So rewriting, the equation in this new form. We have x minus 2 squared minus 2 times y double prime minus 6 times x minus 2 times y prime, and then plus 4 times y is equal to 0. Now, if we think about what our special case was, our special case required that first term to be of the form 1 plus alpha times x minus 2 squared. So our special case requires the first term to be in the form one plus alpha times x minus x naught squared, that whole thing times y double prime. And in this case, we can do that by dividing by negative 2. So we can force this form by dividing by negative 2. And so what we wind up getting then is we have 1 minus 1/2 times x minus 2 squared. This whole, that all multiplying y double prime. Then plus 3 times x minus 2 times y prime minus 2 times y is equal to 0. So in this case, we have our alpha is negative 1/2. Our beta is 3. Our gamma is negative 2. And of course, our x naught is equal to 2. So we get the solution. So finding the solution, we have y is equal to the sum from n equals 0 to infinity of a sub n times x minus 2 to the n, where a0 and a1 are in the real numbers. And then a sub n plus 2 is equal to, we do negative. Then we had, again, alpha times n minus 1 plus beta n plus gamma all over n plus 1 times n plus 2 times a sub n. And of course, our alpha is negative 1/2. So we have a negative out front. Then negative 1/2 times n minus 1. Our beta is 3, so plus 3n. And then minus 2. All divided by n plus 1 times n plus 2. And then multiplied by a sub n. If we wanted to, we could find the first few terms, and so in terms of a0 and a1, I'm not going to worry about that in this case. But this is our solution. We didn't have to run through the whole algebra for the series. We just were forced to rewrite things in terms of x minus 2 for polynomials. Again, even if our equation does not take the form of our special case, this trick of rewriting the polynomials in powers of x minus x naught is extremely helpful for when we go about substituting in the various derivatives of our power series. That way, when we multiply in by the x component, we are just adjusting the powers instead of complicating the polynomial. But this is how we can go about using that special case general solution to solve some differential equations with power series.